Something is moving on Mars, and nobody will tell you what it is. NASA has photographs of something moving on Mars right now, today, in the current Martian summer, and after 15 years of watching it happen year after year, they still will not tell you what it is. Not because they lost the photos, not because the cameras broke. The cameras are working perfectly. Right now, a spacecraft the size of a school bus is orbiting Mars roughly 250 miles above the surface, carrying the most powerful camera ever sent to another planet, and it has been photographing this thing every single Martian season for going on 2 decades. The images are sitting in a public archive. You can download them yourself. And what they show is something that by every rule of physics should be completely impossible. Dark streaks, hundreds of them, some as long as a football field, some stretching for nearly half a mile. They appear on the steep slopes of craters and canyon walls when the Martian summer begins. They grow. They creep downhill. They behave exactly the way water behaves when it flows down a hill on Earth. And then, when the temperature drops and the Martian winter rolls in, they fade away like they were never there. And then, without fail, the next Martian summer comes and they are back. Same slopes, same spots, same behavior, every single year. Now here is why that is so hard to explain. Mars is not a place where things flow. The average temperature on the surface is around -8 degrees Fahrenheit, and that is on a warm day. The atmosphere is so thin that it contains less than 1% of the air pressure we have here on Earth. If you poured a glass of water on the Martian surface, it would not pool or trickle or run. It would violently boil into gas in a fraction of a second and vanish. That is what Mars does to liquid water. It destroys it instantly. And yet something is moving down those slopes every single summer. The question of what that something is has split the scientific community in half, triggered one of the most dramatic press conferences in NASA history, produced papers arguing passionately on both sides, and somehow ended with the most important spot on Mars being the one place we have deliberately chosen never to send a rover. Not because we cannot get there, because we are choosing not to. And the reason they give for that choice is the very thing that makes these streaks so exciting. We will get to that. But first you need to understand the camera that found them, because without that camera, none of this would be a story at all. The most powerful camera ever sent to another world. In August of 2005, NASA launched a spacecraft called the Mars Reconnaissance Orbiter. Strapped to its side was an instrument called HiRISE, which is short for High Resolution Imaging Science Experiment. The name is extremely boring. What it can actually do is not. HiRISE can photograph objects on the surface of Mars, roughly the size of your kitchen table, from 250 miles up. Think about that for a moment. If you stood in your backyard right now and looked straight up into the sky, the height at which this camera is flying is more than 3 times higher than most commercial airplanes cruise. And from that distance, it can resolve something the size of a dining room table. It has photographed the Curiosity rover from orbit. That rover is roughly the size of a small car, and in the image it looks like a tiny blue dot at the end of a long trail of wheel tracks stretching through the dust. For nearly 20 years, this camera has been humanity's high-powered eye hovering over the surface of another world. And in 2010 and 2011, it found something that nobody on the team was looking for. His name was Lujendra Ojha. He was a 21-year-old undergraduate student at the University of Arizona, working in the lab of Alfred McEwen, the lead scientist for the HiRISE mission. Ojha was doing what undergraduate students in science labs do. He was running comparisons between images taken of the same locations at different times of year. Routine work. Tedious work. The kind of work that feels like it matters very little until the day it suddenly matters enormously. What he noticed, buried inside image after image, was lines on the slopes. Dark, narrow streaks only a few yards wide, running downhill from the rims of craters. In photos taken in the Martian summer, the streaks were there, dark and distinct. In photos taken in the Martian winter, they were gone. In photos taken the following summer, they were back. Right there, same place, almost the exact same shape. He flagged them. He showed his advisor. McEwen looked at the data and they pulled images from dozens of other sites all over Mars. The pattern held everywhere they looked. These things were showing up on warm, sun-facing slopes during the warm season, growing downhill over weeks and months, then vanishing when the cold came back. They named them recurring slope lineae. Scientists call them RSL. The rest of us can just call them the dark streaks that move. Now stop and think about what that actually means. Here is a planet that has been described by scientists as a frozen, irradiated desert, a place that has been geologically quiet and basically dead for billions of years. And here are features that behave like they are alive, features that follow a seasonal cycle, features that grow and shrink in response to temperature, features that start at a fixed point at the top of a slope and move downward, just like a liquid would. If you showed those same images to a geologist and told them they were taken in the American Southwest, that geologist would look at you and say you were looking at a small spring-fed seep, a trickle of water coming up through the rock and running down the hillside. They would say that without hesitation. But this was Mars, and Mars is not supposed to do that. For the next 4 years, the team at the University of Arizona kept watching. They documented RSL at more and more sites, not dozens, hundreds, scattered across the planet, concentrated in certain latitude bands, showing up on slopes that got direct sunlight during the Martian summer and nowhere else. The behavior was consistent everywhere. Grow in summer, fade in winter, come back next summer, like clockwork. But behavior alone was not enough. Any good scientist will tell you that something can look like water without being water. To really prove what was happening, they needed chemistry. In 2015, they got it. And what followed was one of the loudest scientific announcements of the last decade. The press conference and the quiet that came after. On September 28, 2015, NASA held a live press conference that was broadcast around the world. Major news anchors covered it. It trended on every social media platform simultaneously. The scientists on the panel included Lujendra Ojha, now a graduate student at Georgia Tech, who had spotted the original streaks as an undergrad years before. What they announced was this. Using a separate instrument on the Mars Reconnaissance Orbiter called CRISM, which is essentially a spectrometer that reads the chemical fingerprints of light bouncing off the Martian surface, the team had found hydrated salts sitting right inside the dark streaks, and only inside the streaks, and only during the times the streaks were active. Not just any salts, perchlorates and chlorates, magnesium perchlorate, magnesium chlorate, sodium perchlorate. These are the kinds of salts that, when they mix with water, dramatically lower the freezing point of that water. A brine made from perchlorate salts can stay liquid at temperatures as low as roughly -90 degrees Fahrenheit. That is well within the temperature range actually measured on Martian slopes during summer. The hydrated salts were found only when the seasonal features were at their widest, which suggested that either the dark streaks themselves or the process that forms them was the source of the hydration. The announcement was worded carefully, as NASA announcements always are, but the implication was impossible to miss. Liquid water flows on Mars today. Not in the deep ancient past, not locked under miles of ice at the poles, not in some theoretical underground lake far below the surface. On the visible, photographable surface of the planet, right now. In images taken that year and the year before and the year before that. Every newspaper on the planet ran some version of the same headline. Mars has water. Maybe Mars has life. And now you need to understand why that second part matters so much, because it is the key to everything that happened next. Here on Earth, life shows up in places that would make your skin crawl. Bacteria have been found thriving in pools of acid stronger than battery acid. They live inside salt crystals in the Atacama Desert in Chile, which is the driest place on Earth outside the polar regions. They have been found in water so salty that nothing else can survive in it. They live in boiling hot springs. They live in the frozen rock of Antarctica. They live in water laced with toxic chemicals that would kill you in seconds. The reason scientists get so excited about liquid water, even briny, salty, toxic, barely there liquid water, is that on Earth, wherever liquid water exists in any form, life finds a way to use it. That is not a guarantee that it works the same way on Mars, but it tells you that the question is worth asking. If the dark streaks on Mars really were the result of salty water seeping through the surface dust, then for the first time in the history of planetary exploration, we had identified a specific location on another planet where you could theoretically land a rover, drive up to it, drill into the soil, and have a real chance of finding something alive. That is a staggering thing to say. And for a few weeks in the fall of 2015, it was the most talked about scientific discovery on Earth. And then, very slowly, almost without anyone noticing, the story began to change. Other scientists started raising objections, not to the raw data, The salts were real. The streaks were real. The seasonal pattern was real. Nobody disputed any of that. What they disputed was the interpretation. And the institutions that had been so confident in September of 2015 suddenly developed a very strong taste for caution. The first problem was the water source. If these streaks were genuinely caused by liquid water flowing through the soil, that water had to come from somewhere. Mars does not have rain. It does not have rivers or lakes or glaciers at the relevant latitudes. Where was the water coming from year after year, in sufficient quantities to drive features stretching for hundreds of meters? No one had a good answer. The second problem was the behavior of the streaks themselves. When researchers looked more closely at where they formed, they noticed something uncomfortable. The streaks only appeared on slopes steep enough for dry sand to slide under gravity. They never crossed flat ground. They never spread sideways. They never pooled. Real liquid water, even extremely thick and salty liquid water, would behave differently. It would seep into lower areas. It would leave wet stains and mineral deposits. It would not stop exactly where the slope angle dropped below a certain threshold. But these streaks did exactly that, every time. In 2017, a team at the United States Geological Survey published a paper arguing that the streaks were not wet at all. They were dry, granular flows. Tiny avalanches of very fine, dark sand, sliding downhill in a way that no one had quite figured out how to explain yet, but definitely not driven by liquid water. The salts in the soil were still there. They were just sitting in the soil already, not actively bringing water to the surface. The lead scientist on the HiRISE mission, Alfred McEwen himself, would eventually say that in his opinion, none of the wet hypotheses had survived scrutiny. And just like that, the story that had dominated global science headlines was quietly downgraded. Not proven wrong exactly, just reframed. Not definitely water, probably dry sand, possibly some combination of both. The scientific community moved on to other things, and most people stopped paying attention. But the streaks kept moving. The debate that will not end. Here is what makes the Mars streak story genuinely strange, and why it has refused to die even after a decade of scientists trying to close it. Both sides have good arguments. Both sides have data. Both sides can point to images from HiRISE showing exactly what they want to show. And no single explanation has ever managed to account for every observation at every site. Some streak sites show clear chemical signatures consistent with the presence of water. Others show no such signatures at all. Some streaks grow in a pattern that looks exactly like a slow fluid seeping downhill. Others grow in a pattern that looks exactly like a pile of dry sand slowly sliding. Some appear on slopes that face the sun and get warm enough for brine to form. A handful appear on slopes that face away from the sun and stay cold enough that any liquid water theory falls apart completely. A definitive explanation for the formation of these features is still lacking, and both the dry and wet theories have their own limitations. It is likely that the formation of the streaks is the result of multiple mechanisms working together at different sites and in different seasons. In 2025, a team from Brown University and the University of Bern used machine learning to build the most comprehensive map of Martian streaks ever assembled. They analyzed over 86,000 high-resolution satellite images, creating an unprecedented global catalog containing more than 500,000 streak features across the planet. Their model favored dry formation processes, and they found no direct evidence of water driving the streaks. That was one of the biggest studies ever conducted on this topic, and it landed firmly on the dry side. But in the same year, another team published a completely different analysis in Scientific Reports, a journal owned by Nature, one of the most respected scientific publications in the world. Their time series study of specific crater sites found a significant increase in streak activity following a massive global dust storm, and the patterns showed a strong dependence on surface temperatures on sun-facing slopes, consistent with the behavior you would expect from liquid water. They also found a landslide near a heavily streaked region that may have been caused by groundwater pushing up from below, destabilizing the slope and triggering the slide, which would suggest that water is moving underground right beneath the surface. Two major studies, same year, same phenomenon, opposite conclusions. This is not a case of bad science. This is a case of a genuinely strange planet that is refusing to be simple. And the fact that scientists have been staring at these things with the best camera ever sent to Mars for 15 consecutive years and still cannot agree on what they are should tell you something. Mars is doing something up there on those slopes that does not fit neatly into any category we have. There is also one more twist that almost nobody talks about, and it might be the strangest part of this whole story. In late 2025, a separate team published a study in Nature Communications looking at seismic data from Mars. Not streak data, earthquake data, or Marsquake data technically. And what they found was remarkable. Seasonal patterns in Marsquake activity suggest the possible presence of near-surface liquid brines confined to depths of just a few meters below the surface in certain regions of Mars. The seismic data showed Marsquakes going quiet during the coldest periods, and then coming back sharply when temperatures rose, which is exactly the pattern you would expect if underground water was freezing and thawing with the seasons. Underground water, freezing and thawing, seasonally, on present-day Mars. If that is real, then the debate about the surface streaks takes on a completely different shape. Because if there is liquid water just a few meters below the surface, in certain seasons, in certain regions, then maybe the surface streaks are just the visible tip of something much bigger happening underground. And yet we still have not sent a rover to look. The rovers that will not come closer. Right now there are 2 rovers driving on the surface of Mars. Curiosity has been roaming around since 2012. Perseverance landed in 2021. Both of them are nuclear-powered. Both of them can climb significant slopes. Both of them carry drills capable of boring into Martian rock and scooping up soil samples for chemical analysis. They are, by any measure, exactly the kind of machines you would want to send to investigate a mysterious seeping feature on a Martian slope. Neither one has been sent to an RSL site. NASA's Planetary Protection Office has indicated it may block any visit to the streak sites because the rovers were not fully sterilized before launch, and the streaks may represent environments where life could currently exist. This is the rule called planetary protection, and it is worth taking seriously before you dismiss it. The idea is simple. If there is even a small chance that the Martian streaks are wet and habitable, then any rover we send there carries a real risk of contaminating that environment with Earth microbes. Every spacecraft we build, no matter how carefully we clean it, carries thousands of hitchhiking bacteria and spores from our own planet. Most would die quickly in the radiation and cold of Mars. But perchlorate brines can protect against radiation. Cold temperatures slow microbial death. And if even one Earth microbe survived long enough to get into a wet Martian environment and start growing there, we would have made the greatest scientific question of our time permanently unanswerable. We could never tell the difference between life that evolved on Mars and life that we accidentally imported from Earth. The planetary protection rules draw their legal weight from Article 9 of the 1967 Outer Space Treaty, which requires nations to avoid biological contamination of other worlds. The global scientific body that oversees planetary exploration updated its guidelines in 2023 to require that all potential landing sites be assessed for microbial risk, and the streaks on Mars have been flagged as areas where this assessment must be done before any rover is allowed in. That is a legitimate reason to be careful. But here is where it gets uncomfortable. The rule that prevents us from investigating these sites up close is triggered by the possibility that they contain liquid water. The question of whether they contain liquid water is the exact question we need to go there and investigate up close in order to answer. We cannot study them without risking contamination, and we cannot know if contamination is a real risk without studying them. We have built a perfect circle that keeps us at a safe distance from the most important square mile in the solar system. The Curiosity rover has actually driven close enough to see the dark streaks on the slopes of the mountain it has been climbing. NASA engineers were forced to plan a diversion to keep the rover away from them. The concern is not just about contaminating Mars. It is also that a rover could be lost on a slope that is too steep, in an environment that is too harsh, on terrain that is completely unpredictable. And so the cameras keep watching from orbit. The streaks keep appearing every Martian summer, and the rovers keep their distance. There have been proposals for future missions. A region called Coprides Chasma, part of the enormous canyon system of Valles Marineris, has been studied as a potential landing zone for a future dedicated mission to the streak sites. The concept is straightforward enough. Land near a streak, drive carefully toward it, drill into the soil at its edge, run the chemistry, get an answer. The technical challenges are real. Most of the streak sites form on slopes too steep for any current rover to climb safely. Dust storms in those regions can be severe. Cold nights can threaten power systems. Planetary protection rules complicate every step of the planning process. But the science is there. The desire is there. The streaks are still there. And the man who first spotted them back in 2010 and 2011, a young undergraduate running routine image comparisons in a lab in Arizona, is now a planetary scientist at Rutgers University. He has spent more than a decade carefully, methodically, scientifically chasing the implications of what he noticed on a monitor one afternoon in his early 20s. The question that drove him then has not been answered. If anything, it has been deferred indefinitely. Notice that pattern. Because Mars has been doing this for a very long time. In the 1970s, the Viking landers ran experiments specifically designed to detect life in Martian soil. The results were ambiguous and strange. The mainstream scientific consensus settled on a negative answer. The lead experimenter, Gilbert Levin, spent the rest of his career arguing that the data actually showed something real and biological. That debate never officially closed either. In 2015, NASA announced that liquid water flows on the Martian surface. By 2017, the leading explanation had shifted to probably dry sand. By 2025, new studies were arguing back in the direction of water again. Every time the conversation gets close to reaching a conclusion, something pulls it sideways. Maybe that is just how science works. Maybe extraordinary discoveries on other planets really do require extraordinary amounts of patience before they resolve into clean answers. Maybe there is no story hiding inside the bigger story. Or maybe we have built a system that is genuinely excellent at spotting tantalizing things on Mars, and genuinely bad at allowing itself to follow those things all the way to a conclusion that would change everything about how we understand our place in the universe. The probe is still up there right now. The Mars Reconnaissance Orbiter has been capturing images of the streaks continuously from 2006 through 2024 and beyond, and researchers using machine learning have documented them across more than 2 million individual photographs. The seasonal patterns are as consistent as ever. Appear in summer, fade in winter, come back the following summer. Year after year after year. Whatever is happening on those slopes, it has been doing it long enough that the college student who first photographed it is now a mid-career scientist with a lab and graduate students of his own. It has outlived multiple missions, multiple theories, multiple rounds of headlines and retractions. And it will keep happening with or without us, every Martian summer, on every sun-facing slope where conditions are right, until someone finally decides that the answer is worth the cost and the risk of actually going to get it. The great open question of Mars has always been the same one. Was there ever life there? That question gets a lot of attention. It gets missions and funding and press conferences about ancient riverbeds and fossilized microbial mats that may or may not have existed 3.5 billion years ago. But the dark streaks are asking a different and more urgent question. Not was there ever life on Mars. Not, did Mars have oceans a billion years before complex animals evolved on Earth? Something moving on the surface of Mars right now, in this season, in this year, is asking whether there is life on Mars today. And we have been choosing not to answer it for 15 years. Every Martian summer, on a slope that should have been dead and still for billions of years, something slides downhill. It dries. It fades. It waits. And the following summer it comes back and does the same thing again. Patient and completely indifferent to our debates about what it is. That is the strange gift that Mars keeps giving us. Not answers, just enough motion, just enough mystery, just enough reason to wonder why we keep choosing to watch from a distance, when the question is right there, a rover's drive away from being answered. Thanks for watching. If you found this as mind-bending as I did, hit that like button and subscribe so you do not miss what comes next. Turn on notifications too, because the next one is going to be just as wild. And tell me down in the comments, do you think those streaks are water, or do you think Mars has been fooling us this whole time?